Hello, my name is Joe Stitt, and I'm representing my group today in being able to present the Identifying Geologic Facies through Seismic Dataset Transfer Learning using Convolutional Neural Networks project. And so let me start that today. And so just to kind of give a little background, our first goal with this project is to input 3D seismic slices like the one we see here, which for our project is from our first data set called the Parihaka from the coast of New Zealand. And again, input this into a semantic segmentation type of architecture, which we see here, which is going to be UNet, and ultimately predict different rock layers or facies on the surface based upon the inputted seismic image, which you see here with each color representing a different facies. Now, there are examples in the research community of this being successful, which you will see we were successful of as well. But our second goal of taking the weights and biases from this first model that we see here and applying it directly to the training process of a completely different seismic data set, which in this case is the F3 Netherlands data set using transfer learning, is something we definitely wanted to explore. And using the baseline parameters to help train and predict facies in the new data set with only given a few number of examples, let's say 10 to 100, which isn't really much for deep learning, and having a successful outcome is something that, to our knowledge, has barely been successfully done and explored in the geoscience community. And it will definitely be the first time this has been completed between the two data sets that we used here, which are widely used in other applications in the geoscience community. And with the transfer learning process comes tuning with the amount of freezing layers, as well as the number of input images. And with a successful model, we will be able to get predictions hopefully close to the one that we see here with the second data set, which here's an example of the predictions from the Parihaka. So again, from the F3 Netherlands data set. Again, here's the Parihaka, here's the F3 Netherlands data set examples. And so by training our baseline data set, the Parihaka data set, we were actually able to predict the locations and extents with high accuracy facies within the subsurface, with an example here to justify that. And the test data we had for this didn't come with any labels, but we can definitely confidently say that after looking at the full 3D volume, these facies definitely match up at around 95% accuracy to the trends that we have seen in the entire 3D seismic volume. Thus, we felt good about the model we tuned and transferred its parameters to the learning process based on the second data set, the F3 Netherlands data set located in the North Sea. And so with the results of that here, so in this process, we had to tune our learning rate, number of epochs, number of frozen layers, and input examples to find the best prediction scenario with a limited number of input examples to make this transfer learning process justified. We will start this movie of slices based on only 100 training and validation examples inputted with our 3 convolutional layers that are unfrozen in this case. And we actually obtained an 81.78% dice coefficient based on our test data set. And overall, we were able to accurately predict the near surface layers, which on average were able to be highly accurately predicted, with many of the complex, deeper facies were predicted fairly well as well. And then finally, the cream of the crop here, with only 10 training examples inputted for this example that we see here, we found very promising results where predictions don't overfit like we've seen in previous iterations, and we get predictions with a general outline of all the facies layer and the layers itself. And with only 10 training examples at 78.57 dice coefficient, these are very promising results and show high potential with data set to data set transfer learning if you're only given a few training examples to train off of.